Welcome to lecture 12. Today we're talking about decay rates, and we will talk soon about cross-sections as well. But fundamentally what we want to achieve is finding observables so that we can predict based on our quantum field theory calculations and compare to experiments. So what is it that we measure? For example, option 1 is that we observe a number of particles and count the number of decays and then divide by the time over which we observe to obtain a decay rate. Yeah, we can call it gamma, and it has the units of per second, decays per second. So in natural units, the mass dimension of this is 1, as it's the unit of inverse time. A second option that we will discuss in the next lecture actually is colliding two particles, or more, but it's simpler to control if you collide two particles with momentum P1 and P2, and then you count the particles with momentum Q2 and Q1 and Q2 that go out into a solid angle of an annulus phi. Typically this process is phi symmetric, but then it might depend on the outgoing angle theta. And counting those particles can tell you something about the properties of the incoming particles, namely about their so-called cross-section. This is something we will consider next time. So now let's start first by looking at the decay process. So we have some initial state and the particles decay into a final state. We can define a probability by saying, yes, we want to have the transition matrix element between the initial and final states with the S scattering operator S that we have discussed and learned how to evaluate. We take the absolute value squared of it and normalize it to the norm of the final and initial states. Now we know that the initial states, just as for any multiparticle or multiparticle state, has a relativistic normalization, as we learned before, and since we evaluated at one point, we get a delta function evaluated at 0. We know that if we put the system in the box, all the delta functions at 0 that give you in principle a divergence are actually just volume factors. So this factor here just becomes a volume factor times 2, twice the energy of the initial particle. In principle, we could have a product here of all possible initial particles, but since we are only looking at the particle that decays into some number of final particles, this index is just 1. It's just 1 energy. Here, the final particles might be plenty, so we have to take the product of all in the normalization of all possible final state particles. And another key simplification is that in the rest frame, the energy of the initial particle is just the mass of that particle. Now let us evaluate this object here. So we see the in the momentum notation, this transition matrix element is the momentum transition matrix element that we know our Feynman rules for. We have the 2 pi to the 4 factor. We have the momentum conserving delta function, as well as, since we have a product of those two, a second 4-dimensional delta function that in the box just becomes a volume times time. Yeah, it's a 4-dimensional volume. So it's 3 volumes times time in this notation. Here we have, for the initial state, we have the 2m times volume that cancels 1 volume factor, and the product of over the final states and the volume factor are given here in the denominator. So in addition, we can, or we have to integrate, if we look at if we want the total final state, if we want the total transition probability into a final state, we have to integrate over the phase space, so namely the volume elements of the momenta of the final state particles and their and an integral over the volume itself. Since the expression doesn't depend on any x variables, this integral over the volume just gives you a volume factor that cancels another factor of the volume. And what we end up with is the transition matrix element times the momentum conserving delta function times the product, that it's just a notation whether we write this product here in the numerator or can pull it out and write it here, times the product over all final state momenta and the two EF factors, yeah, just give us the Lorentz invariant measure, combining it with the momenta of the final state of particles. So now we can actually define a phase space measure with these factors, the product over the final state, and the momentum conserving delta function as d pi n, where n is the number of final state particles. Yeah? So that will be the product over n final state particles here, and it will contain those delta function plus the 2 pi to the 4 factor. Having that, we have a very complex expression for our decay rate, where we take the probability to decay and divide it by time, and we get this decay rate gamma. So we have 1 over 2m times the volume, or the phase space measure, times the transition matrix elements squared. And now if we want the total decay rate, we integrate basically over the phase space measure, and we sum over all possible final states. So we have this kind of continuous integral plus and the sum to just take into account all possible pathways that the particle might, if the particle, for example, decays in 2 and 3 and 4 final states, we will have to sum over all possible final states while integrating over the phase space for each of them. So now let's not make it too complicated and take a simple example where we have a two-body decay of particle, scalar particle phi, that decays into two charged scalar particles psi bar psi. And let us define also the final, the total momentum squared, and call it S. And we can now rewrite our momentum phase space measure for two particles. We just write down the definition, the two integrals, and the delta function, and then we use this identity for the delta functions that we also use to derive the Lorentz invariant of the measure to show that the momentum, the basically one-dimensional energy and time part of the delta function can be used to incorporate these factors of 1 over the 2 energy into the delta function, and making it then into a delta function that takes into account the momentum squared and the mass squared here. So we can rewrite this measure as having a delta function in it. Well, we just basically fix Q0 to E, which is just a physical requirement, and then we rewrite it with the means of the identity above as a four-dimensional integral with this Q squared delta function, fixing the Q squared to its mass shell to be equal to the mass squared, again, just a relativistic requirement. So that with this trick, we can rewrite this measure, rewriting one of the delta functions in this way, and then evaluating the integral that we have, getting rid of one of the delta functions, and just getting replacing basically Q 2 by P minus Q1. Yeah, this is this delta function is being used to replace this Q2 by P minus Q1. And now we can also choose the center of mass frame, where we have the spatial momenta of the outgoing particles to be equal to opposite in direction. P, the incoming momentum, is just square root of S, as we defined it above, P squared being the total energy squared S. And we can simplify our expression, P minus Q1 squared minus M squared. Going through the algebra, we get this expression here, S minus 2 square root of SE1 plus M1 squared minus M2 squared. Substituting the whole thing in here gets us this expression here for the momentum product and for the momenta. And now we can also transform the measure, making use of these identities here to know how the measure and how the energy and momentum related. We can check how the measure transforms and rewrite our measure. Just have a look at the derivation. It's actually just using spherical coordinates and applying the differential identity above here. Introducing this into the expression, we get a simplified expression here, where we basically can evaluate this expression, noticing that there is no dependence on the angular variables, and evaluating the E1 integral. And that only sets essentially the delta function to 1, leaving us just with a Q factor here. And yes, with a Q factor here, and then from this integral we get just 1 divided by square root of s, just by the delta function identity here, that if you have a delta function of a function, we know that it's a delta function of a shifted variable x minus x naught, where x naught is the 0 of the function g divided by the derivative of the function g, the modulus of the derivative. So if the function g of v1 is the argument of the delta function here, we know what its 0 value is, so we know what actually x naught is this function, and g prime is just 2 times square root of s. So this expression is just this expression, e1 minus this x naught here, the 0 of the g function, divided by square root of s times 2. So evaluating this just leaves us with a square root of 1 over square root of s times 2, and the other thing is just trivially satisfying the theta function identity, setting the theta function to 1, which is, again, just a physical requirement. So finally, for our purposes, we have found that our phi decay is the matrix element that we put in from the quantum field theory calculations using the Feynman rules, q over square root of s. And when we use the relativistic kinematics, we find that this q factor divided by square root of s, the total energy, is just 1 minus 4 times m psi squared minus m phi squared. So this basically would also write as 2 times m psi over m phi squared, right? This is just an energy condition that tells you that the 2 times m psi have to be smaller than m phi for the decay to be possible, just in terms of energy conservation. So that's really straightforward. Now, for our example here, we can recall that this matrix element is just a simple IY, so the squared is just the y squared divided by 2m. If we, for example, had set the mass of the psi particles m psi to 0, this square root is just 1, and we have a very simple expression with units of energy, inverse, no, it's units of energy and units of inverse time as expected. Y has the units of energy in our theory, if you remember. Now, if we take, for example, m phi to 1 GeV and y to 0.1 GeV as a reasonable perturbative value, we get something like 10 to the minus 4 GeV for the decay rate, which is of the order of 10 to minus 21 seconds, which is in the ballpark of strong decays, like quantum chromodynamic decays of, for example, a delta resonance that can decay into a proton into pi 0. So that is a physical fast decay process, and that's expected since we're talking about this theory with a relatively large coupling. So even in QCD, the decay rates are rather fast. That again tells us that it's a potentially strongly coupled theory as opposed to weakly coupled theory, like weak decays take much longer times, or electromagnetic decays where the coupling is an order of magnitude smaller than this coupling strength. The electromagnetic coupling in this kind of, to compare it to those units or to this coupling, the electromagnetic coupling is about an order of magnitude smaller, making all the decay amplitudes at least 2 orders of magnitude slower as the coupling enters the theory in the squared form. So that's it. This is the basic derivation of the decay amplitude. We found how to connect the kinematic observable of the decay of the particles per unit time with the amplitude that we calculated from quantum field theory, basically just from the Feynman diagram phi going to psi bar psi, which is just given by the IY Feynman rule, and that's the simplest quantum mechanical amplitude that we have evaluated in different ways. That immediately gives us an observable rate that we now can, on the other hand, use by just measuring the decay rate, counting the decays of particle per unit time in seconds, let's say, and convert it then into the expression that would, for example, allow us to extract the value of y being 0.1 GeV, for example, if we were to observe this process here. And this, in this way, we could learn something about the Lagrangian interaction term, which, as you remember, has the negative y phi psi bar psi term. So there is a direct connection, again, between the Lagrangian of the scalar Yukawa theory and physical observables. That's it for today, and next time we're going to talk about scattering processes and how to connect them with quantum mechanical amplitudes.